Okay, let's get screen sharing happening. All right, do you see my screen, Karen?
Yes.
All right, great. And I'll put on captions.
Can I record this?
I actually am recording, but you are welcome to do that as well.
We'll have a backup then.
Sweet. All right, I'm going to get started. Thank you, Karen, for that wonderful introduction, and thank all of you for coming to watch me present about my thesis research on landslides in northeastern Minnesota. This is an inventory mapping and susceptibility assessment project that I've been working on with Karen and a large group of collaborators for the past 2 years, and I'm really excited to share some of our findings with you today. And so just a little context and motivation for the study as to why I study landslides in northeastern Minnesota. And it's for many of the reasons you would want to study them anywhere else in the world. When landslides and similar mass wasting events intersect with public safety, infrastructure, and water quality, they become a serious hazard. And this is part of a larger statewide mapping effort with several colleges and universities, as well as collaborators at the USGS, to actually figure out where have slope failures occurred in the past, and can we actually predict or create a susceptibility model for where they're likely to occur in the future. We actually have additional motivations for studying landslides in Minnesota, and that's because past research has been very geographically biased to mountainous and tectonically active regions across the globe. And I really like this figure because it depicts, it's from a review paper of 565 articles on landslide susceptibility mapping from 1983 to 2016. And you can just see how that geographic bias in the research. And though there have been studies done in the United States, those are also focused mostly on mountainous areas in Washington, Oregon, and California. And so this is not so much research has been done looking at the relatively flat landscape of the central lowlands of the United States or the upper Midwest. And so that's what we hope to assess here in this research. Additionally, we actually have really great access to state data here in Minnesota. And there was a 500-year flood event that occurred in 2012, and high-resolution LiDAR data had actually been collected in the spring of 2011. And so following that flood event that occurred in June of 2012, where 20 to 25 centimeters of rain fell over 48 hours following one of the wettest Mays on record in Duluth, so that the already high soil or elevated soil moisture conditions were allowed for hundreds of landslides to actually be triggered as a result of this precipitation event. And there was a huge push after the flood event to collect repeat LiDAR in the fall of 2012. And some of the USGS collaborators on this project are actually working to untangle some alignment issues and work on doing some change detection and object-based image analysis with that data. So now that I've established the motivation for looking at landslides in northeastern Minnesota, I'm going to outline the questions that this study hopes to answer. And so firstly, more broadly, we're looking at where do slope failures actually occur in northeastern Minnesota? And we'll do that through our inventory mapping phase of the project. Secondly, what are the factors that are driving slope failure in this area? And can we create an effective predictive model using spatial data that's available to us? And lastly, how does scale and geomorphic setting actually influence the performance and transferability of that predictive model? So a really general overview of our regional geology, we're looking here in the Lake Superior watershed in Minnesota. And I love the way it's described as being forged by fire and ice, because the bedrock geology of the area is actually a lot of igneous and metamorphic rocks from a failed mid-continental rift system that occurred about 1.1 billion years ago. And so you have a lot of igneous, intrusive, and extrusive rocks that form the Duluth complex and the North Shore volcanic group sequences, as well as some older Precambrian sedimentary and metasedimentary rocks in the southwestern portion of the watershed. But what's really interesting, to me at least, is the more recent glacial history, which represents the ice portion of our geologic history, where the Laurentide ice sheet has advanced and retreated several times over the past million years or so, with the last glaciation receding about 11,000 years ago. And that ice has scoured the landscape and redeposited glacial sediments in different depositional environments. And it gives us the surficial geology and topography that we have today. And there are also some processes that are still at play here following deglaciation. So we're actually in a relatively young landscape, geologically speaking, and we get to see and observe all of that landscape evolution as a result. And so as those ice sheets were retreating from the landscape, the meltwater would coalesce into these large basins. And so about 11,000 years ago, the meltwater from the Laurentide ice sheet actually filled the Lake Superior, the modern Lake Superior basin, and it was at a much higher lake level, and so we call that lake Glacial Lake Duluth. And there were several fluctuations in the lake level of Glacial Lake Duluth, and so we have different names for those. And what's interesting about this is that those adjustments in lake level actually set off a wave of midpoint migration in most of the tributaries to the basin. And so there's a high degree of channel incision that's generated a lot of relief closer to the lake, and lower relief has occurred upstream where that midpoint migration has not yet quite propagated into the headwaters. And so keeping that in mind, actually also there's another process known as isostatic rebound that is at play still. And so isostatic rebound and isostatic adjustment is essentially crustal uplift from the release of pressure that was imposed on Earth's crust from these massive ice sheets. And so where the ice sheet was thicker, there was more pressure on the crust, and once all of that was released, it actually rebounds faster where the ice was thicker and less fast in areas where the ice sheet was thinner. And because of that, you get differential uplift that actually has impacts on lake levels in Lake Superior, leading to lake level rise in areas closer to the St. Louis estuary. And so our study area is the Lake Superior watershed. Because we had such a broad area to cover, we had to be strategic about our remote mapping to get all of it done. And we observed from previously documented landslides in the area and from what we know about the processes at play that streams and river corridors are very important, as well as the Lake Superior shoreline. So all of the areas here outlined in orange are places that we actually remotely mapped. And the areas in purple in this smaller inset map on the right-hand corner are places that we were able to field verify. So last summer I went out with a team of undergraduate research assistants, and we actually walked a lot of these paths. And we also used a canoe and small fishing vessel to get at some of the coastal slides and slides along the St. Louis as well. And so when I talk about inventory mapping, I'm talking about cataloging all of the landslides into a geodatabase of polygon features. So when you're doing landslide mapping, you have to assume three things. First, that landslides actually leave discernible scars on the landscape that trained geomorphologists can recognize, classify, and map. And secondly, that these landslides are the results from physical processes that are governed by physical laws and thus produce different discernible morphologies. So different landslide types are going to actually manifest differently in the topography, and that similar types of mass movements will produce similar signatures. And so we can actually classify the slope failures that we're mapping into different categories. And there is actually a lot of subjectivity in landslide polygon mapping, and to eliminate some of that subjectivity, we followed Oregon and Washington state protocols for mapping landslides using LiDAR data. And we also adapted their geodatabase schema to match our needs in Minnesota for this project. So like I said, slope failures can actually be further classified by the way that they move and the material that is moving. And so when we went out into the field, we took pictures of all the different landslides that we field checked. And here's a sampling of the most common landslide types that we observe in northeastern Minnesota. So we're seeing a lot of shallow translational slides that have a planar surface in the glacial material. We also see these rotational earth slides that have a curved failure plane and multiple slumping blocks. And up the North Shore, where you have these steep near vertical bedrock cliffs, you end up with rock fall and rock topple zones. And in glacial lake sediments that are very clay-rich and silt-rich, there's a process called liquefaction that occurs, where when moisture is introduced to the substrate, it will actually flow like a viscous fluid, and that's where you get these earth flow morphologies. And so our inventory actually ended up being about 2,000 mapped landslides across the Lake Superior watershed. And during our field verification season, we were able to check 35% of those. And our field verification revealed that our mapping had about 97% accuracy, which gave us pretty high confidence in our mapping, in our remote mapping. We noticed that there is a higher density of landslides in St. Louis and Carleton counties, especially, and because Carleton County is actually an area that was previously occupied by Glacial Lake Duluth, and so there are a lot of glacial lake sediments there in that area that are now being incised through by the evolving river channels. And we noticed that most of these are rotational and translational earth slides that are proximal to river channels and the Lake Superior shoreline. And they are occurring in these glacial lake shoreline deposits and lake sediments. So to get at slope, at landslide susceptibility, you have to understand the balance between the forces that are driving movement and promoting downslope movement, that is known as the shear stress of the material, and the resisting forces that deter that movement. And so there's a term in engineering called the factor of safety that essentially captures the balance between these two forces in terms of the shear strength and shear stresses. And there are several parameters that actually go into this equation, such as the slope angle, the density of the material, material thickness, cohesion of the material, the intrinsic properties of that substrate. And because we don't have site-specific data to assess these parameters, we need to figure out what spatial data sets can actually capture or represent these parameters. And so I'm explaining all of this to you as sort of the basis for why we're choosing morphological and geoenvironmental variables in our susceptibility analysis, such as things like slope, depth to bedrock, land cover, and distance to stream. And I'll talk more about those in a little bit. So now that we have this database of 2,000 mapped landslide polygons across the Lake Superior watershed, can we actually use that information to create a susceptibility map that predicts where slope failures are likely to occur in the future? And because slope failures are likely to occur under the same conditions that led to past instability, we can actually capture and assess those conditions by looking at what factors are primarily driving slope instability. And there are several methods of doing this. And we decided, or I decided, to choose a classical statistical approach called the logistic regression analysis. And what it does is very similar to a multivariate linear regression, except your outcome is binomial. You either have a landslide or you don't. And so this method predicts the presence or absence of your dependent variable, which is landslide occurrence, using a set of predictive independent variables. And it requires some data prep and coding, and I worked in ArcGIS and our statistical software to compile the data sets needed and run the analysis. And then we went back into ArcGIS to actually generate the susceptibility map itself. And in a logistic regression analysis, any value over 0.5 is considered a landslide, and anything below is considered not a landslide. So I'm going to actually walk you through a case study in Jay Cooke State Park, which is an area in Carleton County which was heavily impacted by the 2012 flood event. And so we're going to be using 2011 LiDAR to get at those pre-failure conditions. And then we're going to, once I've walked you through all of those steps, we're going to apply the same methodology to a larger study area, the Lake Superior South watershed, to compare how different study areas of different scales and different geomorphic settings perform with this methodology. And then we're going to apply those models that we've created to the Mission Creek watershed, which has not had a logistic regression analysis conducted in it. And so this is a visualization of the morphological variables that we used. So we included slope, aspect, and relief, which are all raster derivatives from the 2011 LiDAR, and the depth to bedrock layer we got from the Minnesota Geological Survey state data. We also used the Minnesota Geological Survey substrate information. We used Surgo data for our soil erodibility factor, which is the K factor value that gets at soil textures. The land cover was taken from the National Land Cover Data Set, and we used 2011 to keep that consistent with our pre-failure LiDAR. And we also included one explanatory variable, which essentially is assessing the proximity to a feature that might be important in terms of landslide susceptibility. And so other studies have used things like distance to faults and distance to roads and distance to streams. And so we decided that distance to streams is definitely something we want to look at in these areas. And so now that you have all of these great raster data sets, we need to somehow extract information from them and put it into a format that can be used in statistical programming software. So I cast a fishnet of points across the study area, and the points here in green represent areas that are stable and have not had landslides occurring in them. And so I sampled stable conditions from that fishnet. Then I cast a denser fishnet of points over our landslide polygons to extract information about the local conditions in our unstable areas. And that allows me to compare stable and unstable areas in the logistic regression. So I'm going to take you through the steps that I used to put together this model, and then we're going to look at how we generated the map and compare the models to each other. So the goal here is to create a susceptibility model that is as accurate as possible, but also not overly complex. And so we're going to try and eliminate variables that are irrelevant to the analysis or that might skew or bias our results. And so the logistic regression does not like variables to be overly correlated with each other or highly correlated. So we ran a correlation matrix to look at the relationships between our variables. And we see that the only real concern is between relief and slope, which appear to be highly correlated to each other. And so because slope is an intrinsic part of slope stability, we chose slope over relief and eliminated relief from our analysis on the basis of our correlation matrix. Second, you want to make sure that you are comparing like variable types. And so we have substrate, which is a categorical variable with classes such as sand, clay, and silt, and bedrock. And slope, which has values, it's a continuous variable with values from 0 to 71. And so to compare apples and apples, we converted our slope and other continuous data sets into categorical information by binning them into geometric intervals, which have a similar number of observations in each category. Then you want to make sure all of your factors, all of your classes are well represented by your data. You're going to randomly subdivide the data into 80% training and 20% test data sets so that you can check the accuracy of your model with data that was not used to train the model. We used the mass package to run our generalized linear model with the binomial aspect, and we used a stepwise function called step AIC that's going to run different combinations of your variables and choose which model actually has the best fit. And we use something called the Akiake Information Criterion, the AIC score, which rewards models for goodness of fit, but penalizes them for being overly complex. And so we actually input the test data into that model that we've generated to create something called a confusion matrix that will assess model accuracy by looking at the balance of false positives and false negatives. So to explain the confusion matrix, I ran a simple logistic regression in R with slope as our only predictive variable. So this is the model summary results that you'll see from a logistic regression. It has your coefficient estimates, which weigh how much each class influences slope stability or instability. Having higher positive values means it has a higher contribution to slope failure, and having higher negative values means it has a higher contribution to stability. And then you've got your standard error, your z-value, statistics, and the p-value, which is your statistical significance. And so when you look at the logistic regression curve, which doesn't look very much like a curve here because this is just one categorical data set, you can see that our false positives are any points that were actually stable conditions, but the model predicted to be a landslide. And then we've also got our false negatives down here, which are landslide points that were predicted by the model to be stable. And when you look at the balance between those, you can actually calculate model accuracy. So for slope as the only predictive model in this logistic regression, in Jacob State Park, that model actually had 81.4% accuracy, which is really high for just having one predictive variable in your model. We also observed some variability when randomly subdividing our data. And so we decided to analyze that variability by randomly subdividing our data set a bunch of times. And so we ran multiple iterations of our model, each with a different random sampling of training and test data. And we did that 1,000 times so that we could look at what variables are only included some of the time and not always chosen as significant influencers to the model. So when we ran those 1,000 iterations, most of our variables were always included using the step AIC function. However, aspect appears to only be significant in 40% of our models. And so on that basis, we decided that aspect wasn't contributing enough to the models, and we used that as a justification to remove it. And we ran an additional 1,000 iterations with aspect no longer included in the model so that we can choose out of these 1,000 models the best fitting model to build our susceptibility map with. And so we use that to find our final model. And here's a histogram of all of the AIC scores from all of the iterations. And we're going to choose the lowest AIC score because that represents the one with the best fit and least complexity. So to get from your model summary results that look like this table up on the top right corner here, you're going to be focused on your coefficient estimate to get that into ArcGIS and to a map format. So to do this, I created weighted rasters using the reclassify tool and assigned these coefficients as the new raster pixel values for each of our data sets, for each variable that was included in the analysis. Then that allows you, with these weighted rasters, to run a raster calculation that performs the logic function and creates a map that essentially has landslide susceptibility in terms going from 0 to 1, 0 being low susceptibility and 1 being high susceptibility for a landslide occurrence. And this is what the map in Jacob State Park actually looks like. So once you have that information from 0 to 1, you can classify it however best suits your needs. And so we used 3 susceptibility classes here, low, medium, and high, and classified those using the natural breaks method in ArcGIS. And slope, land cover, depth to bedrock, and distance to stream and substrate were all variables that went into this model. And when looking at the confusion matrix, we see that this model accuracy is 82.3%, which, if you recall, the slope model on its own actually got us to about 81% accuracy. And so the addition of 4 other variables actually didn't do a whole lot for predictive accuracy, but just slightly constrain the model a bit more. So now we can move into a larger watershed and a slightly different geomorphic setting. So this is more of an ice marginal setting here, whereas the Jacob model was run in sort of glacial lake sediments and shoreline deposits. And when we look at the Lake Superior South model, we see that this larger watershed actually performed with 95.3% accuracy using slope, substrate, soil K-factor, depth to bedrock, and distance to stream. And so that model actually performed better than the Jacob model And then we want to see if we can transfer those model results into a watershed like the Mission Creek watershed, which is about the same scale as the JCOOC model and a similar geomorphic setting. And so it's not surprising that the JCOOC State Park model actually performed really well in Mission Creek. But when we tried to transfer the Lake Superior South watershed model to Mission Creek, it did not perform very well because of the change in geomorphic setting and watershed scale. And so now I want to talk about what we can actually take away from all of this and what are the implications of these results. Okay, so when looking at the slope instability factors that came out as important using this analysis, we see that slope is the single most effective predictive variable in this landscape, in these watersheds or study areas. And there might be a strong forcing from the fact that we are using pre-failure LiDAR data and information in an area where most of the events were triggered by the 2012 event. And so in most studies, they're forced to use post-failure LiDAR or measure adjacent slopes to get at those pre-failure conditions. And so we might be capturing slopes that are slightly steeper because they're prior to failure. We also see that in post-glacial landscapes, depth to bedrock, distance to stream, and substrate are important to consider because they were included in both of our models. And there is a little bit, it's difficult to tease out which of these are more important because, say, with substrate, and we know that a lot of the slope failures are occurring in glacial material. And is that because the glacial material is intrinsically less stable, or is it because that's where river incision is happening and they're happening and the slope failures are occurring along those stream and river channels? So it's a little more difficult to tease out which variables are actually the causal factor or having more influence. So now some of the really cool implications of this research is that climate change projections suggest the area is going to have, that we're going to have warmer and wetter conditions in the future with an increased frequency of high intensity storms. And we actually have the 2012 event, which serves as a good example of how the landscape responds to flooding and heavy precipitation during a wet season. And so using the results from the change detection work that was done as part of this project, I actually looked at how many were impacted, how many of our polygons were impacted by the 2012 event. And we noticed that 60% of the landslides were either triggered or reactivated during the 2012 event. And so if projections for a wetter and warmer climate with high intensity storms is accurate, then I anticipate we will see increased slope failures in this area in the future. There are also implications from climate change on coastal erosion. And so the increase of high intensity storm events means the increase of wave action along our shoreline. And when you also have high lake levels, that exacerbates that wave action on coastal, the effect of wave action on coastal erosion as well. And so looking at this figure on the right here, the squiggly green line actually represents lake level change over the past 100 years. So we do experience natural oscillations on a near decadal scale of lake level. And we are currently, as of 2019, in a high stand. And so lake levels are actually elevated right now. And as a result of isostatic rebound in the Duluth area, we also have higher lake levels because of that isostatic, that differential uplift causing higher lake levels closer to the St. Louis estuary. And so all of that is potential to exacerbate coastal erosion that we're seeing. And the city is actually struggling a lot with maintaining infrastructure in the face of these increasing storm events and coastal erosion. And so in conclusion, we see using our inventory mapping results that we do have a good understanding of where landslides have occurred in northeastern Minnesota. The multivariate logistic regression analysis can provide a reliable susceptibility model, but there are limitations when choosing your study area scale and location. Slope is an effective predictive model on its own, but depth to bedrock, distance to stream, and substrate should also be considered when looking at slopes in post-glacial landscapes. And that climate change projections should contribute to mass wasting, and this must be considered when making management decisions to protect people, property, and Minnesota's natural environment. And since susceptibility work is a huge part of the larger collaborative effort of our project, I put together some recommendations based on our research for susceptibility work in other parts of the state. And so from my experience, we see that the number of landslides is a limiting factor for the size of the study area used in a susceptibility analysis. And therefore, if you have high density of landslides, you're able to use a smaller area, but in areas where landslides are more sparsely spatially located, you're going to require a larger study area to do your analysis. Also, slope, depth to bedrock, distance to streams, and substrate are critical variables to consider when studying landslides in these young, previously glaciated areas. And thirdly, geomorphology matters. To improve the predictability of your model, study areas should perhaps be chosen not based on state or county boundaries or state park boundaries, but more so focused on the geomorphic boundaries and watershed boundaries that seem to perform better. Also, there's a lot more that can be done using the data set that we've created with our landslide inventory. This study did not have the opportunity to look at precipitation, and we have enough information using the change detection work and our inventory to do an event-based model that examines precipitation from the 2012 event and how that impacted landslides in the area. Also, we did not conduct detailed monitoring, and this research does not replace or supplement the need for site-specific assessments in the areas that have been mapped as high susceptibility for landslide occurrence. And lastly, our landslide geodatabase is simply a snapshot in time of the past and present slope failures. And so in order for this resource to remain relevant and useful to emergency managers and the public, it needs to be maintained and added to. Just because this project is coming to a close doesn't mean that slopes are going to stop failing. And so my hope is that somewhere on the state level, an agency will take on this database and continue to grow it and add to it so that it remains useful to the people of Minnesota. And with that, I will thank Karen and my committee members and all of my undergraduate research assistants and people that helped contribute to this project, and my funding, which was the Legislative Citizens Commission on Minnesota Resources. So thank you all.
Thank you so much, Emily. And so we have a chance now to take some questions from the audience. If people want to turn their videos back on so they can smile and wave, feel free. If you have a question, you can either put it in the chat, or you can raise your hand, or if there aren't very many all at once, go ahead and unmute yourself and ask a question. I will ask that the committee members hold off until we've had a chance to have other people ask questions.
Hey, Emily. It was really an awesome presentation. That's such a lot of work that you did. It's so useful. I'm really impressed. So my question is, like for somebody who has, property or like a cabin or something in this area, is it something that they could kind of go and look at? Are they at risk? And like, is somebody going to be using this to kind of go and evaluate property potential damage?
Yes, that's a great question. This resource definitely has the potential to be used in that way. We hope that once it's made it through USGS review, it will be released electronically and accessible by anyone. And so I would encourage that that private landowners would look and see if their land and their property is at risk, And also in the planning of new infrastructure and property, I would hope that it could be used to prevent future infrastructure damage. And so, yeah, I hope that that is the way that it is utilized.
Any more questions?
Yeah, I had a question.